All right. Good afternoon, everyone. So my name is Sergey Kopasov from University of Edinburgh. And so first, I'd like to thank the organizers for inviting me here and organizing such a great, very interesting conference. And so the topic that the organizers wanted me to talk about are the hypervelocity stars. And I think this topic fits really well with this theme of finding rare gems. And so I think this topic will be probably more focused on kind of, I guess, science and less so on technical detail, and kind of will be somewhat, I guess, my view on this kind of quest for finding this particular type of rare gem. But hopefully it will be still, it will be kind of useful as a kind of possible lessons we can take from this particular search. So first, I will start with a bit of introduction. And so here we're interested in finding particularly high velocity stars in the Milky Way and what kind of mechanisms can produce such high velocity stars. And in general, there are kind of, roughly speaking, three main mechanisms that can produce kind of fast stars in the Milky Way. So one of those is basically so-called runaway stars mechanism, where basically you can have kind of star cluster, young star cluster, you have a lot of binaries there, and those binaries interact, you have kind of chaotic encounters, and then you can easily basically eject individual stars with the velocity of easily a few hundred kilometers per second. So this type of mechanism won't be the main focus of my talk, but I know this can produce reasonably fast stars. So another mechanism, which also not going to be the topic of my talk, but also can produce quite fast stars, are the set of processes involving supernovae, especially supernovae in a binary. So you can have, for example, supernovae type 2 in a binary, and after the explosion, obviously the companion will potentially fly away, or you can have let's say double degenerate pair, so basically pair of white dwarfs orbiting each other with mass transfer, and one white dwarf, if it experiences the thermonuclear explosion, basically another white dwarf can easily be ejected with really high speed and will have very weird elemental abundance on the surface. So this particular type of high velocity stars have been actually recently found. This is a set of papers by Shen and Al-Badri, who used the Gaia data and the promotions and parallaxes to identify this kind of fast-moving stars. However, the main topic for me for today will be a different mechanism, the so-called Hughes mechanism. And so just a kind of reminder what this mechanism is, basically the idea is that if you have a supermassive black hole, like we do in the Milky Way, you have a binary star that come close to the black hole. Basically, it can get tidally disrupted, and one of the stars get captured on the eccentric orbit, and another star is ejected with the speed of basically a few thousand kilometers per second. And the ejection speed is basically a simple function of the orbital speed of the binary around the black hole and the orbital speed within the binary. And yeah, so if you plug in the numbers for what's possible, say, in the Milky Way, the mass of the supermassive black hole in the Milky Way, you basically can easily produce stars ejected with a few thousand kilometers per second through this mechanism. And so basically, for the purposes of this talk, I'm going to call hypervelocity stars the stars ejected through the Hughes mechanism. That's what we're going to be after. So basically, what we're going to look for, we're looking for stars with really high velocities, so potentially, ideally, larger than the escape speed at a given point in the galaxy. And also, we want stars where basically the orbit points directly at the galaxy center to be sure that this is indeed a Hughes mechanism ejection rather than something coming from just a disk runaway star. And so initially, this Hughes mechanism is kind of pretty old, was introduced in the 80s, and kind of not many people were, I guess, kind of interested in it. But then in the first kind of accidental discovery, and we're going to have quite a few in this field, in the work by Brown and collaborators, they basically were trying to probe the velocity dispersion in the Milky Way stellar halo. So they targeted blue horizontal branch stars selected from Sloan Digital Sky Survey. And when they measured the velocities of that sample, they basically noticed that there was a star with the speed of 700 kilometers per second. which is clearly, so the star was at a distance of about 100 kiloparsec, and at that distance it's clearly above the escape speed of the galaxy. And not only it's above the escape speed of the galaxy, also it turns out to be basically young B-type star, and with a lifetime kind of comparable to the flight time from the galactic center to the current position of the star. So they basically immediately attributed this kind of star to the Higgs mechanism, and this kind of led to many follow-up studies, basically trying to find more of these types of objects, including studies by Brown and collaborators with the MMT survey. And the idea what was done there is to look in particular for basically like B-type stars in the stellar halo. It's not like we had an expectation that all the hypervelocity stars must be B-type, but it's simply caused by the fact that if you want to spectroscopically follow up, the Milky Way stellar halo has a lot of A-type stars, the blue horizontal branch stars. So if you want to limit your follow-up to just a kind of small subset of objects, we're basically forced to select B-type stars. And so in this particular search, they basically found a handful of more objects, and you can see the kind of the plot here showing the velocity versus distance, and the stars showing individual stars they've seen. You can see noticeable error bars, and the dashed line here shows the escape speed of the galaxy. And the point here, we have the stars sitting above this line. So that makes them possible hypervelocity stars. But you already potentially see a problem in this, because we have the majority of stars in the Milky Way sit way below this line. They have much lower velocity, and the error bars here are large. So when you're trying to find this kind of stars that just sit above this threshold, and you have way more stars sitting below the threshold, you kind of have to be careful that you're not just observing kind of just random noise scatters above your threshold. And it turns out that basically when the Gaia data came about, Gaia 2 in the first instance, when we start to get basically parallaxes and proper motions for a larger number of this stars, it became possible to reevaluate the status, whether those stars are indeed bound or not bound. And so this plot basically shows the kind of each point here is an individual star, and on x-axis is probability of bound before we had Gaia data, and on y-axis is probability bound after Gaia data. And basically it turns out that a large number of stars turned out to be bound after the Gaia data came about. So basically the illustration of the effect that I just talked about on the previous slide. And not only many stars turned out to be not to be hypervelocity stars, also if we look in detail how constrained those orbits are for hypervelocity stars, it turns out that even the ones that are consistent with the galactic-centric ejection, if you look at the region of the galaxy where they could have been ejected, it's still extremely large, basically comparable to the whole Milky Way to the whole Milky Way disk. But Gaia not only allowed to kind of undiscover some hypervelocity stars, but also enabled some kind of potential discoveries. Obviously, Gaia provides us with the parallaxes, proper motions, and many people did the kind of exercise of just looking at, say, total 3D velocity, plotting it against galactic-centric distance here. And so you have the bulk of stars sit at low velocity. You can draw a curve, the escape velocity curve, and you can basically try to look at stars sitting above the escape speed. But again, you have this kind of problem that you have basically millions of stars sitting below this curve and substantial error bars. So again, you're in danger that many of these candidates would be just kind of scatters from this bulk of the distribution. Furthermore, the escape curve itself is kind of not super well known, because even the mass of the Milky Way been changing very recently by significant factors. So and also this Gaia 6D searches were kind of limited by basically the volume where you have a good Gaia parallaxes. So, okay, so this was the state when kind of Gaia and Gaia 2 came about. And so the kind of to go into the next stage of my story, I want to talk a tiny little bit about another rare gem, which kind of play the role in the next part of my talk is, so this rare gem are the stellar streams. So we heard a little bit about the stellar streams in the very first day of the conference. Basically, stellar streams are just result of the disruption of globular clusters and dwarf galaxies. around the Milky Way. And maybe 20 years ago, those stereo streams were really rare gems because we only knew about a couple of those. But in last years, basically, as we start to get deeper and deeper data, the number of known streams grew, and especially with the arrival of Gaia data, where we start to be able to discover a large number of those streams. And so one thing that came after this discovery of large number of streams is we started to need to do a lot of spectroscopic follow-up of the streams to basically get radial velocities in those streams to get good orbits of those streams. And this basically led to one particular project that I've been involved in, the S5 project. It was mentioned on the first day. S5 stands for Southern Stellar Stream Spectroscopic Survey. This is a project led by Ting Li, who is a faculty at the University of Toronto. And the goal there was basically try to observe with AT, with the 2DF instrument, all the stars in the stellar streams that are observable from the south. So basically, we tried to observe about 20 stellar streams. Spent about 100 nights, I think, by now on this. But one important fact of this survey was that because it was done at the time of Gaia, and for most of our stellar streams, we knew the proper motions, we could basically very efficiently select our stream stars. And that meant that basically we had a lot of spare fibers. We didn't kind of need all the 400 fibers available to us in 2DF. And so we basically could include a large number of spare fibers for additional targets. And the additional category that we included there was basically blue horizontal branch, the blue category, which included blue horizontal branch stars, blue stragglers, and white dwarfs. And that's what turned out to be interesting for this talk, because when we obtained a large fraction of the data from this survey, we started to look for various kind of outliers, looking for spectral outliers. But one of the outliers we looked as well was the outliers in velocity space. And to kind of our surprise, we saw this star, which we call S5 ES3S1, which basically the spectrum you can see here at the very bottom, it turns out to have a radial velocity of 1,000 kilometers per second. And also it turns out to be at the really nearby and very bright at 16th magnitude and 8 kiloparsec distance. And then if you convert this the proper motion in distance to the total 3D velocity, you basically get 1,700 kilometers per second, which is obviously well above the escape speed. And so because the star is so nearby and we have basically full 6D, we can take this star back and integrate it back to like a galactic disk. And so when we do that, basically we get this picture. So this is just a picture of the galactic disk, where the galactic center is this black dot in the center, the sun is here, and the red, barely visible ellipse is the region where we can trace this 5 HVS1 is coming from. So it's basically, the stars come from spot on the galactic center. It's a really tiny region around it. And we can basically figure out that the ejection speed from the region around the black hole was probably about 1,800 kilometers per second. So it basically makes it really confident, make us really confident this is an ejection through the Higgs mechanism. And it's kind of worthwhile to compare this to other hypervelocity stars that kind of known at the time. So here, kind of the same plot as I had on the previous slide, but now extending to from minus 30 to 30 kiloparsecs, and different ellipses at different stars traced back to the galactic plane. And the S5HS1 is this barely visible red ellipse. Everything else, you can see how enormous those are. So although many of these stars are consistent with the galactic centric ejection, I know we're not really confident that they are coming from the galactic center. And so before kind of moving forward, I also want to just maybe give a bit more science motivation why we actually care about having those kind of like a small number of stars directly associated to the galactic center. So the reason why we're kind of excited about this is because we think that the properties of this hypervelocity stars are telling us something deep about what's happening in the region around the black hole. Because, for example, like most of you know that around the black hole, we have this S-star cluster. So it's a cluster of young B-type stars on eccentric orbits. And we don't quite know, I guess, the origin of all these stars, but there's one theory is that this S-star clusters S stars are basically produced through this hypervelocity star process. So where the binaries were coming towards the black hole, one star was ejected, became hypervelocity stars, and the partner star basically became trapped on eccentric orbits. And that's what we see there. So by probing the hypervelocity stars, we're really learning something about this process, and we hopefully can find out where these binaries that fell on this supermassive black hole, where they're actually coming from. Also, one can say that because the process of creating hypervelocity stars is kind of similar to creating TDEs, if we constrain the rate of hypervelocity stars, we also learn better what's the rate of tidal disruption events in the Milky Way, for example. So this is kind of additional motivation to look for this kind of stars. But also, I want to say that this accidental discovery of this kind of record-breaking star that is 15th magnitude is kind of disconcerting. It kind of potentially tells us that we're not doing a good enough job, that we just accidentally stumble upon this kind of record-breaking stars. And so the next kind of two results that I'm going to talk about are basically a result of this kind of thinking what we can do better to potentially find all of this really extreme types of stars. And so all this work I'm going to present later is work by my PhD student, Silver Barron, who is a PhD student in the University of Leiden. And so one of the things that always is was limiting the searches for hypervelocity stars is basically availability of kinematic information, because pretty much that's the only thing that really determines whether something is hypervelocity star or not. And if you think about how many velocities we have in the Milky Way, the best case is Gaia RVS, which provides 30 million radial velocities. But that's still, the sample of stars which Gaia RVS probes is pretty bright, 16th magnitude. So we really like to be able to get radial velocity for a much larger set of stars. And one thing that we thought about is, could we actually use the Gaia XP spectra, really low resolution spectra, to get radial velocities for potentially 200 million of stars? Because that would really enhance the volume that's available for us. And so we heard already talk about the Gaia XP in the first day of the conference. So not going to talk much about it, but just going to show a few examples of spectra. So this is a Gaia XP spectra of a hot star. This is a Gaia XP spectra of cool star. And it turns out basically you can get reasonable velocities from the spectra after some work. So here at the bottom panel, this is an illustration how the radial velocity errors change as a function of the color and magnitude. So blue here is roughly 200-ish kilometers per second. Obviously, by kind of galactic dynamics standards, 200 kilometers per second, that's useless. But here we're talking about finding stars with maybe moving with 1,000, 1,500 kilometers per second. 200 kilometers per second is fine. And basically, for cool stars on the right, we're getting about 200 kilometers per second. And that's not surprising, because the spectra for cool stars basically have a lot of molecular features that are very informative. And in the blue, you have Balmer break. So again, for the blue stars, we also get pretty high accuracy. But in the middle, we basically, the accuracy is not good enough because you have no features. So in theory, that can work for hot and cool stars. And so we run this analysis to try to find possible hypervelocity stars. Unfortunately, as in many of these kind of searches, when you look at things in the tail of distribution, you really very sensitive to outliers from like a bulk of the population. And it turns out that at least in the DR3 version of the Gaia XP, the quality is just too many outliers. So right now, this search, we're not able to basically find anything new. But the hope is in DR4, this search may actually yield hopefully some new hypervelocity stars. So this is a kind of first project done by Sil. So a second project that the result of this will be on archive probably next week is kind of thinking again about this case of this S5 HVS1 star that we found. So this is a star really bright, kind of hyperpromotion. What could have we done to find it before just accidentally stumbling upon it? And it turns out that if you basically decide that you're just looking at stars ejected from the galactic center, you can really use the fact that you are looking at stars with orbits that are basically pointing towards the galactic center. And it turns out that if you look at those kind of stars, if you know the proper motion and position of star in the sky, you can basically determine from basic geometry what's the distance to the star and what's its radial velocity. just based on this assumption of coming from the galactic center. So you have this implied distance basically available for every star in Gaia, and then you can use this implied distance to say, put star on a chart diagram, see where it's in the wrong place. If it's in the wrong place, you don't care about those stars. You can also compare this implied distance to the Gaia parallax. Again, if it doesn't match, not interested. And then you can also select basic stars that have implied velocity larger than 600. And it turns out that if you do that, basically for the stars brighter than 19, in Gaia, you basically get 600 candidates, where S5HUS1 is one of the top candidates. And so what we've been doing last year, basically, we tried to follow up these stars. We followed up about 200, and you don't need really kind of very sophisticated follow-up, just really low resolution, low signal intelligence will do it. So unfortunately, like among the 200 we followed up, none of those turned out to have the right velocity to be hypervelocity stars. So in this case, it was not, the search was not successful. So the only thing I guess we could do in this case to put limits on the kind of rate of the ejection of hypervelocity stars. And it turns out that, I know this plot here at the top shows the kind of limit, red line shows the limit on the ejection rate. We basically could say that the ejection rate of high velocity stars is lower than 10 to the minus 5 solar masses per year, which is roughly maybe order of magnitude better than was available before. We can also use this result to better understand what we actually expect to find, like let's say in the whole Gaia. For example, from this analysis, we basically predict that the whole Gaia should have probably about 20 unbound hypervelocity stars, and basically the majority of them should be like massive main sequence stars. And that's kind of unfortunate because like basically if those stars are massive and main sequence stars, that won't really tell us much about, say, mass function, which is sensitive to kind of physics of what's going on in the galactic center, or I won't know much about ages, because for ages it would be nice to have like giants, for example. But like if we think now about what kind of future surveys will be available in the future, one thing is definite that when, say, OSST or Roman will come about, what we're going to get a large number of proper motions available down to, I don't know, whatever, 24, 25th magnitude, and that will basically enable us to discover some of the low mass hypervelocity stars. So, and basically, because right now, our current Gaia volume is just too small, we really don't capture any low mass hypervelocity stars. But with the OSST and Roman, I think we most likely will find low mass hypervelocity stars, and that will help us understand better constrain the kind of physics of ejection. Also, we obviously going to have the large spectroscopic surveys. We have, I know, DESI that's operating now. Foremost, we're going to start soon. And I think here again, we have to take some lessons in terms of designing the best way of designing the kind of spare fiber program, because we can now, I think, target this kind of objects much more efficiently, and hopefully significantly increase our number of known hypervelocity stars. Another thing which is kind of exciting that I know in principle is possible in the future, it would be cool if we start to find hypervelocity stars that originate not just from the Milky Way, but actually from other nearby galaxies. Because, for example, for the Large Magnetic Cloud, we don't even know if the supermassive black hole or intermediate mass black hole is there. And so if we find stars associated with the Hughes mechanism associated with LMC, that tells us that the black hole is there. So at the moment, there is maybe one star potentially associated with LMC, but it's not quite clear if it's exactly Hughes mechanism or not. And also, in fact, it's actually possible to look for hypervelocity stars associated with M31, and you can kind of do it in a couple of ways. You can either just imagine large area survey, deep enough survey of the area around M31, for example, with Roman, and there, let's say the star like S5HUS1 will have magnitude of about 25. So you would just need to look for basically blue things in the halo of the M31, at 100 kiloparsecs. Basically, the most likely reason why the blue stars will be there is through the Hughes mechanism. And also, another way of potentially detecting stars through the M31 ejection is you can just, some of the stars ejected from M31 could be found in the Milky Way itself. And there are some calculations predicting where they should be and what's their properties. So I think that's, quite exciting of what was possible in, I think, probably next few years with these future surveys. So, okay, so now let me kind of conclude. Hopefully, I convinced you that the hypervelocity stars, I think, truly kind of needle in a haystack problem. Here, we're talking about kind of 1 star per billion or maybe 100 million types of stars. I think the hypervelocity stars are really telling us some important things about the physics of what's happening near the galactic center. So I think we really want to increase our samples from basically 1 to the number that can be called statistics. And then I think now we finally start to be able to design, I think, much more efficient way of looking for these stars. And hopefully with the, say, low resolution Gaia data in DR4, we will be able to basically probe 200 million stars or maybe 300 million stars to look for hypervelocity stars there. And that's everything I want to say. Thank you.